So we ventured into chapter 13 and we are working on functions of several variables. We just got started and I like this question maybe. I hate to take all your fun away. This is, yeah, that's okay. I'll take this fun away from you here. So I'm in 13.3 and I found this problem number 70, which gives me a function of two variables. A function of two variables actually equals a third variable. This is f of xy equals 3x cubed minus 12xy plus y cubed. 3x cubed minus 12xy plus y cubed. And what we learned right at the end of class, I mean, we learned how to take partial derivatives. If I want to do a derivative, I can do a derivative of this function with respect to x, which means I hold y constant and take the derivative as if x was the variable and y was a constant. Or I can take the derivative with respect to y, vice versa. Y is the variable, treat x like a constant. And we talked about kind of what that means as far as the slope in the direction of the x-axis or the slope in the direction of the y-axis on this three-dimensional surface. So those are all good ideas. I just summed up pretty quickly there. Sometimes we use the word slope. Sometimes it's convenient to think of derivatives as a rate of change. I mean, which is the same thing, but it's the rate of change of one variable with respect to another variable. I don't know. It's just depending on the problem. Maybe the word problems you tend to think of a rate of change. And then there's other problems where you tend to think of derivatives as slope. Anyway, this number 70 says what? Up at the top it says, find all the values of x and y, such that the partial derivative with respect to x equals 0 and the partial derivative with respect to y equals 0 simultaneously. So the question is, find when fx equals 0 and when fy equals 0. And they are using the word and, not or. I think we might have different results if we're using the word or there. So I'm looking at places where both these partial derivatives equal 0 simultaneously. Okay, well, I need a couple partial derivatives. It sure is easy. The partial derivative with respect to x is 9x squared minus 12y. With respect to x, treating y like a constant, we did good. That's good. You guys okay with that? You understand that, I guess? All right, I also want fy, the partial derivative with respect to y. Then this x is treated like a constant, so that's gone. With respect to y, negative 12x, and then 3y squared. Okay, well, that's easy. But now I'm doing this thing where so not only do I want these derivatives, I want to do something with them, and they're asking this question: when do they simultaneously equal 0? So this problem sort of turns into two equations, two unknowns. I'm solving when does this equal 0 and when does this equal 0. Like I just said, sort of two equations, two unknowns. Solve this system of equations in a way. You guys okay with that? Okay, I'm not sure what you're thinking. It's two equations, two unknowns. I guess I would solve and substitute somebody. I think maybe I'll try to solve this one for y. I'll tell you what, I'll add the 12y over here, equals 9x squared. I'll divide by 12. 9 divided by 12 is 3/4 x squared. So I just solved for y there, I guess. And then I'll substitute that in for this other y over here. This is interesting. So I get 0 equals negative 12x plus 3 times this y. Y is a 3/4 x squared. Hold on, that's my y. And then I have to square it. And so now I'm solving this equation. Okay, I got it, I think. This is a negative 12x, and that's a 9/16. When you multiply by 3, I guess it's 27/16 x to the 4th. All right, you guys, we're trying to solve this equation. Any suggestions?
Factor out an x.
Thank you. That is the suggestion, kind of. Factor out an x. Somebody might suggest you could factor a 3 at the same time, but I'm just going to ignore that. I'm going to factor out an x, and I would have negative 12 plus 27/16 x cubed. Okay, so when does this equal 0? Well, when something is factored, of course. You set each factor equal to 0, so one place this equals 0 is when x is 0. By the way, when x does equal 0, let's go back over here. What would y equal? I mean, I'm looking for the partner that goes with x. So when x is 0, I can plug it back in here, and what would y be?
0.
Of course, 0. So we sort of just found one answer. The question was, find the points x, y, where both these derivatives are 0. And so we found one point, 0, 0. The other point we get by setting this other factor equal to 0. When we set this other factor equal to 0, we got a little algebra to do. But it's going to involve some cube root of some sort, I guess. I'll move the 12 over. I'll multiply by 16/27. That'll be my x cubed. Are you guys following me? Yeah, the cube root of that.
192 over 27.
That's 192 over 27.
64.
Not quite. The cube root of 192 over 27. Is that what you just said? The cube root of that. Okay. I know the cube root of 27. That's a 3. I don't know the cube root of 192. Is there one? Probably not. Whatever. The cube root of 192. It's some decimal. It's not nice. I'll just leave it the cube root of 192. Sorry.
Plug that in. Solve for y.
Well, I guess so. Right. So this is my x value. I found this place. Again, I'm looking for my point, and I just found this x value. The cube root of 192 divided by 3. How do I get the y value? You're right. Plug it back in here. I got this relationship. You're right.
Is that just 192 over 9 now?
Well, I don't know. Let me think here. You're right. It's 3/4, and then it's the cube root of 192 over 3 squared. So you have the cube root of the 192, and that gets squared over the 3, which gets squared. You're saying that's just a 9, right?
Yeah.
You can cancel that 3 with that 9. That would be a 3. That would be a 12. So I'm getting the cube root of 192 squared over 12. Yeah, I'm happy with that. I mean, I don't want to get too crazy here. I could work on simplifying this a little bit, but I don't want to. I'm done. I'm happy. That's simplified enough for me. What did I do? I took this x and plugged it in here. X squared times 3/4. That x squared times 3/4. Right? I cleaned it up just a little. That's my y value. So we did it. We found these 2 points. The cube root of 192 squared over 12, I guess, is the y value. You guys all right? All right. That was kind of fun. You know, they asked me these questions for good reasons. They're asking me about when do these both derivatives equal 0. I mean, do you remember from calculus, why would you take a derivative and set it equal to 0? From calculus 1, why would you?
Maximum, minimum.
Yeah, I mean, when the derivative is 0, that means your slope of your tangent line was 0, meaning you had horizontal tangent lines, which usually happen at a max or a min. Right. So we're not really going to yes, we are. At the end of this chapter, finally, at the very end of this chapter, we find maxes and mins. And this is sort of previewing that. I don't know which one's a max or which one's a min. I'm not trying to do that now. But these are good candidates for maxes and mins. You're right. Because we found a place where the slopes are zero. Where these slopes are zero. See, one more time, what we just found was a place where, remember now, this is a curvy function here. This is a surface. And when I stand at a certain point, what I just found was the slope in that direction was 0. And then I also found that the slope in the y direction was 0. See, I found these two slopes are 0. Now, I'm just a little bit ahead of myself when I say, if once these two slopes are 0, every slope is 0. The slope in any direction is 0. So that helps you really think you're sitting on top of a mountain, maybe. I don't know. We just proved that that slope is 0 and that slope is 0. But I'm providing this extra information, which is if those two are 0, every slope in any direction is 0. So we are at the top of a mountain or the bottom of a valley, right? At a max or a min in 3D, max or min. We are. The very end of this chapter, there's a test. It's called the second partials test. We would need some second derivatives, and we could test to see who's a max and who's a min, or who's a saddle point. A saddle point is not really a max or a min. I'm way ahead of myself now. I'm about 2 weeks ahead of myself. I won't get there yet. Anyway, that was good stuff. In 13.3, you're doing some partial derivatives, and in this particular question, you're kind of doing it for a reason. You're looking for these places. You're looking for these points. Okay, listen, I think I want to get into this 13.4. I like this section 13.4. So I think I'll try to get that done today here before we leave. We do have a little shorter class today. In 13.4, the title is Differentials. Oh boy, I almost feel like I want to, I sort of feel like I want to take you back to Cal 1 a second. Listen, I'm going to try this. I'm going to try to take you back to Cal 1 for just a second. Because in my Cal 1 class, I may not have done a great job with this. In somebody else's Cal 1, I don't know. Here's what I want to say. When we do a derivative back in Cal 1, and sometimes we would call it y prime or we would call it dy dx. When you talk about the word differentials, then you're talking about the dy and the dx as sort of separate quantities, and you're trying to define them as little. We think of the derivative as dy dx, like it's one phrase. Dy dx, it is one phrase. It's the derivative, dy dx. But we can make meaning for the little dy and the little dx as separate little differential quantities. By the way, all it is some small change in y and some small change in x. It's really this. The change in y over the change in x, but it's the limit as delta x goes to 0 that sort of makes it turn into dy dx. That's Cal 1 in a nutshell. It's a change in y, a change in x, but let that change in x get very small, and we sort of call it dx, and the change in y got very small as a result, and it's dy. Here's maybe a better illustration. Watch this. Here's sort of a geometric illustration of this. Watch this. So if I have an x, if I have some curve, f of x. Okay, so if I have a point x, I can plug it in, and of course I can get a y value. I'm going to call the y value f of x. Okay, this is sort of a calculus 1 discussion. Watch this. Then you add a little bit to this x. You want to add a little bit. So I'm going to add a little bit to this x. I'm calling that the change in x. and I get to this new point. You know what this new point's called? X plus delta x. Is that okay with you? And then I plug that in the function, and I get that y value. What should I call that y value? F of x plus delta x. And then that's a y value, and that's a y value, and if I wanted to, I could call that the change in y. It really is the change in y. And then there's the change in x, there's the change in y. If you wanted to find that slope, that would be called the slope of what we call the secant line, but it's just the slope between 2 points. It's not the slope of the tangent line yet. I make it the slope of the tangent line by, sort of like I said, you let delta x go to 0, so you let this get very, 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 very small, and then you end up with the slope of the tangent line. Okay, now watch this. I'm trying to get to this. So then I have the slope of the tangent line. Boy, oh boy, here's what I want to say. I want to say that delta y is the actual change in y on the function. It's the change in y on the function. Here's what dy is. Dy is the change in y on the tangent line. So this delta x it's the same. Delta x is dx, is the way we say it. But now watch this. When I plug this point into the tangent line, see this change in y on the tangent line? See that? That change in y on the tangent line is what we define as dy. So we call dx the same as delta x, actually. And let me just ask you something. Look at this picture. Is dy the same as delta y? No. It's different. But dy is a good approximation for delta y. Well, my picture looks like it's not a good approximation, but it's a real good approximation when this change in x gets very, very, very small. I mean, maybe you can see when that change in x gets small, that tangent line and the change in x on the tangent line and the change in x on the function is the change in y on the tangent line and the change in y on the function is practically the same thing. For small changes of x, the tangent line practically is the function. When you get far away, the tangent line is not the function. Anyway, did you ever have that discussion before? And then, anyway, then we would play some games where you would try to use the differential dy as an approximation for delta y. Well, anyway, I'm in chapter 13. I'm in calculus 3, and I'm trying to do this same thing in 3 dimensions. So I wanted to explain this 2-dimensional analogy to you. Maybe try to make you recall it. Again, in my Cal 1 class, I might not have done a good job with this. It just depends. Sometimes I get to where I have to skip this section. But it's worth discussing, and we're going to discuss. And so in 13.4, it's a new idea. What we have is this thing called dz. This dz is called the total differential. It's called the total differential. It's dz, and there's a little formula for it. Here's what it is. It's the partial derivative of z with respect to x times dx plus the partial derivative of z with respect to y times dy. This is a cool little formula. You'll need this on the test in a couple weeks. You'll need this for 13.4 problems. It's very, I like reading this. I think I can read this pretty well, you guys. I can think of this as, this is called the total differential. It's like look at it, it's like a total change in z. And by the way, I drew the straight up d and I draw the little curly D's on purpose. That's not me being sloppy. That's me. That's purposeful. So this straight up dz is actually a change in z. But look what it is. Well, check this out. It's made up of a partial change in z. It's made up of how much you're changing in the x direction plus the rate at which you're changing in the y direction. You know? Or you can think of this as, you can sort of think of this dx as canceling this dx, and you got a little partial change in z, and then cancel these, and you got another partial change in z. Add them up, you got your total change in z. I mean, it's kind of cool to kind of understand this formula to some extent. The analogy to what I just did is kind of tricky, but I'm going to show it to you. You ready? Z is a function of x's and y's. So Z is some surface. That's a surface. And what I have is a little point in the xy plane called x and y. When you plug it into the function, you get a z value. Is that okay with you? All right. If you add a little bit to this x and add a little bit to this y, you might move over here. And what you did was you added a little x plus delta x and a little y plus delta y. You added a little bit to the x, you added a little to the y, so you move to a new point. You plug that new point in the function, and you get a new z. Hang on, I better call this z. I better call this first z f of xy. What am I going to call this second z? Yes, thank you. It was hard to say, that's why I asked you to help me. Thank you. Right, f of xy, plugging in this xy point into the function gives me this z value. Plugging in the new x and y point that changed gives me a new z value. And if I subtract those z values, I have what's called an actual change in z. But what this dz is an approximation for this. The dz we use as an approximation for the change in z. And what this dz actually is, it sure as hell is hard for me to draw this, you guys. The book has good pictures, but I'm going to tell you this. I mean, the analogy is, you're probably about to say it before I say it. There is a tangent plane here. We haven't really discussed tangent planes but there's a tangent plane at this point. Delta z is the actual change in z on the function. dz is the change in z on the tangent plane, analogous to what I just explained 10 minutes ago. So this point, if it's tangent at this point, then this point is on the tangent plane. This point, if I plug it into the tangent plane, maybe it's right here. Look, that change in z is dz. And it's an approximation. I mean, this is a geometrical explanation for what the hell this dz is. And we don't necessarily need this geometrical explanation, but it helps maybe to have some kind of explanation. Otherwise, it's just some formula. But what it actually is it's there's an actual change in z happening. When you move your x and y point, you've changed z. You've changed z, probably. And so there's the change in z on the function. If we calculate this, we're calculating an approximation to the change in z. And it's called dz, and for small values, for small changes in x and y, this will be approximately equal to this. dz is approximately equal to delta z. What I really want to do a problem now. I'm sick of this sort of background theory. Let's do a problem. Did you have a question?
Yeah. That second black dot, why does the surface touch? It touches that black dot?
Well, I'm trying. My surface is an amoeba. Yeah. So I was trying to say that plug this point into the function and you end up a z value on the function. plug this point into the function, and you end up at a z value on the function. My tangent plane didn't have to touch that. No, I got you.
All right.
I got you. My tangent plane wasn't necessarily touching that point at all.
Okay.
All right, there it is. My trapezoidal tangent plane is. Yeah, it's tough, dude. The book has some good pictures. Let's do a problem. So now I like these problems, and I got time for a couple, and they're good. So I think I'll try this. I'll try this 12. 12 looks pretty easy. So I'm in the book. I'm in 13.4, and I want to try this number 12. And number 12 gives me a function. The function is x squared plus y squared. Hey, you guys, without even reading the problem, I don't know, you might not think this is great advice, but without even reading the problem, I'm in chapter 13. I'm learning about partial derivatives. Let me do some partial derivatives. I bet I need them. What is the partial derivative with respect to x, please?
2x.
Good job. And the partial derivative with respect to y? 2y. By the way, I hope you understand my notation. This dz dx is just another way of writing what I wrote over there, f with partial with respect to x, right? dz dy is just another way of writing f partial, subscript y. That's what that notation means, partial derivative. All right, so now up in the beginning part of this problem, I should read it because it says, evaluate f of 2, 1. They want me to evaluate f of 2, 1, and they also want me to evaluate f of 2.1, 1.05. They want me to evaluate f of 2.1, comma, 1.05. You know what they're doing to me, you guys? They've got an original x and y. Can you please tell me the original x and y? I think that would be the 2 and the 1 that they're asking me to plug in the function. But then I think they have a little change in x and change in y. Can you tell me what the change in x is?
1.
Well, x went from 2 to 2.1, so you're telling me the change in x is 0.1. Okay, I agree. Now, by the way, the change in x is also can be called dx. They are the same, and we're calling it 0.1. See, the change in x we call the same, and the change in y is also the same as dy. So what is the change in y, or dy? The 0.05. Thank you very much. Yes. But is the change in z the same as dz? No, that's where the approximation comes in. Now, what they want me to do is they want me to do both. They want me to do delta z, and they want me to do dz, and they want me to compare these. All right, let's work on, delta z requires no calculus. What is delta z? I mean, I can write you a formula, but it's kind of here on the board, or it's actually kind of obvious. I mean, delta z is you plug a point in the function and get a z value, you plug the other point in the function and get a z value, and you subtract that. I guess I could write that. The formula for delta z is f of x plus delta x, comma y plus delta y, minus f of xy. Are you guys with me? Mm-hmm. Plugging in one point, plugging in another point, and subtracting them to get the change in z. There's no calculus on this. This is just plugging in and subtracting. Let's do that. So what is f of 2, 1? If I plug, there's my function. That's pretty easy. 4 plus 1, 5.
Isn't that our initial?
Well,
okay.
I'm plugging in that one, and then it moved. That is sort of the starting one. You're right. I mean, and then it moved to this one. And let's plug in this one. You guys could help me. 2.1 squared, 1.05 squared, added together. .1 squared.
I got a 5.5125.
Okay. 5.5125. 5.5125. And so the actual change in z would be that the second one minus the first one. I hope that's clear. 5.5125 minus the 5, which would be the 0.5125. Awesome. That's the actual change in z. If we calculate this thing, dz, the total differential, then we'll have an approximation for that. It should be close to 0.5125. Let's try it. Here I go. To do the dz, watch this. I guess I can sort of do it in general. dz would be, according to the formula, it's the partial derivative with respect to x, which is 2x, multiplied by straight up dx, plus the partial derivative with respect to y, which is 2y, right you guys? Times dy. Now let's fill in some numbers. What was the original x and the original y? That was the 2 and the 1, thank you, before you moved them. And then how much of a movement was there? What was the dx? The 0.1, and what was the dy? The 0.05, that's right. Fill all that in and you got dz. It's not difficult. In fact, maybe it's easier than doing the other one, but I don't know about that. So here I go. 2, what are we saying? This x is a 2. And the dx is a 0.1. And the 2 is here, and then the y is a 1. And the dy is a 0.05. And so, I think that's a 0.4. I think that's a 0.1.
0.5?
This is just a 0.5. Good. So this dz, when you calculate this out, you're saying it's a 0.5. Awesome. I knew it wasn't the same as delta z. There it is, delta z. I knew it wasn't the same, but I knew it was supposed to be close, which it is. And then you're just calculating these numbers, and they have no meaning to you, except I did give you some meaning. But you can sort of do this problem with no meaning. But what was the meaning? That's the actual change in z. When you move this point, that's the actual change in z. And what's this?
The change in the tangent surface.
It is. It is the change in z on the tangent plane, which is right next to the dang surface. You know, the tangent plane is right next to the surface, especially with these small changes in x and y. That tangent plane is right next to, but it's not the surface. It's a little bit off the surface. And so it's the change in z on the tangent plane is a little different, but it serves as a good approximation.
Why would we need an approximation?
I know, that's a good, kind of a good question. I mean, why am I doing this? The approximation almost seems tougher than the actual thing, because the approximation involves taking some derivatives and doing some calculus. Finding the actual change in z was just plugging in some numbers and subtracting. You know, there's times in higher math where you know about the derivatives, you know about these rates of change, but you don't know about the original function. So there's times when this is all you got to work with. And we present math differently. We present math, we give you the function and say take derivatives. But I think in actual life, maybe you know about the rates of change and you don't know what the actual function is, perhaps. And so you could use this formula without, well, you got to know these rates of change. You got to know these slopes somehow. But you might not know the original function. I don't know. That's my answer. The other thing I like in this section 13.4 is there's some really cool word problems involving error. What we do with this concept here is we turn it into error analysis. And so we have measured values of a quantity. The x equals 2 and the y equals 1 might be the measured values. And then if it was off plus or minus 0.1 centimeter, then that dx, that error of 0.1 centimeter is called dx. If this was off by 0.05 centimeters, then that dy, we call these the errors. Here, let's do a problem. So we use this total differential to approximate error. We do these cool word problems. Check this out. I'm going to do a cool one here. I want to measure the volume of this room. Okay? So it's a big room. I want to measure the volume of this room. By the way, let's assume this room is actually a rectangular solid. Ignore the little drop-down ceiling there. Let's ignore a few. Let's pretend it's a rectangular solid, and I want the volume of this room. So here I go. I'm going to measure it. You ready? Eyeballing this thing. I'm going to say the length is 50 feet. The length is 50 feet. And now that was pretty much an eyeball measurement. I think there was some error involved. Do you agree?
Yeah.
I'm going to say plus or minus 3 feet of error. That's what I'm going to say. All right, now I'm measuring the width. The width is 40 feet. The width is 40 feet. I got a little better view of that, so I'm going to say the error is, I'm going to say the error is 2 feet. I don't know. Okay, the height of this room. I'm going to say the height of this room is 10 feet. That's kind of standard. I don't think there's much error there. I'll say plus or minus half a foot of error. Half a foot of error. Are you guys okay? Now, I want to calculate the volume of this room. So I need a formula for the volume of this room. What would be the formula for the volume of a room?
Length times width times height.
Length times width times height. And what I want to do is, you know this, when you have error in your measurements, then when you calculate the volume, you're going to have error. Error gets compounded in your equations, right? What I want is the error in the volume of this room. I've got error in each of my measurements, so how does that error compound in the volume equation? Well, and then rather than actually calculate what's called the actual error, which would be the change in V, I want to approximate the actual error by using an approximation for the change in V. What do I want to do? I want to do dV. I want to do dV. It'll be an approximation for my error. This will be the error. This will be the error in calculating the volume. Actually, it'll be an approximation for the error in calculating the volume of the room. Are you guys okay with this? dV, the total differential, is going to be an approximation for the error in calculating the volume of the room. That's what we do. That we adapt this formula to serve us in these word problems involving error. All right, this is awesome. You ready for this? There's one thing that happened in this problem, though. Remember, I kind of told you, everything we learn can be, we can have a function of 2 variables, but the formula, we can have a function of 3 variables, we can have a function of 4 variables, we can have a function of 5 variables. I mean, notice this guy. This guy does have 3 variables. So I'm gonna, this formula that I gave you with 2 variables in it just gets adapted, we get added on here, 1 more variable. And so in general, here's the formula for this volume. It's dV dL times straight up dL. And what is straight up dL? That's the error in measuring the length. Plus dV dW times straight up dW. This is me doing the total differential with 3 variables. I have 1 more to do. dV dH times dH. Are you guys all right? Just extended that formula into 1 more dimension, 1 more variable. That's all. That's all. It's that formula extended into, with different letters, different variables, and an extra variable. Okay, so listen. Let's fill this in. This is easy. What is dVdl? What is dVdl? dVdl, the partial derivative of v with respect to L. The partial derivative of v with respect to L.
Oh, wait.
dVdl, the partial derivative with respect to L. So, hang on, with respect to L, you're treating L like the variable, and the W and the H are constants, so his derivative is WH. Is that okay?
Yeah.
WH, okay, so his dV is WH times DL. Plus, I need the derivative with respect to W. The derivative with respect to W, treat W like the variable.
LH.
It would be LH. L and the H are constants multiplied by W is, yes, LH. Times DW. Okay, I'm going to fill these numbers in a minute. dVdH. What's dVdH? dVdH. LW. Yeah, LW times DH. Hey, you guys, we can fill in these numbers. Up above, I gave you this. Now, what did I give you when I gave you that? The actual L, W, and H are those measured values of L, W, and H. What do you think these errors are? That's my DL, my DW, and my DH. And maybe they come with these little plus or minus symbols attached to them. I want to fill them all in here. Can I say something? If I put a little plus or minus 3 right there, and a little plus or minus whatever right there, and a little plus or minus whatever right there, can't I just sort of factor the plus and minus all the way out front? So I think I'll just do that. The answer will have a plus and minus on it, I guess. And I can just fill in these numbers, you guys. This is my DL, this is my DW, and this is my DH. Here I go. This is awesome. DV is, I might have a little room here, W times H times DL. W times, here it is, W and H. That's a 400, and DL was a 3. Plus LH. LH. You guys okay? I think LH is a 500. And DW is a 2. You guys okay? And then LW. 2,000. And DH is a half. This is awesome. This is awesome. DV is this number, 1,200, 1,000, and 1,000. Is that right, you guys?
Yep.
1,200, 1,000, that's 3,200. 3,200 probably cubic feet of error. I mean, that's my error. To tell you the truth, though, it's actually an approximation for the error.
Approximation for error.
Hey, this is a funny question. I'm going to go into just a little overtime here, if you don't mind. Is this good error or bad error? I mean, is that a lot of error or a little bit of error?
I'll say a lot.
Yeah, it looks kind of like a lot. The truth is, you can't really answer that unless you think about what the term, this other term. Okay, so I'm going to point to this and call this error. But to really decide whether it's good or bad, you kind of need to think about relative error, relative to the actual measured actual volume of, and we call that, watch this, we call that dV over V. And again, if you've done some science labs and stuff, you might have put your error over your, I don't know, you might have done some different things, but I'm calling that relative error. And I would like to calculate that now. Well, that's my 3,200 feet cubed over the actual measured volume. The actual measured volume is just length times width times height. And I guess you just use the 50, 40, and 10 as if you didn't have any errors. So the actual volume is 50, 40, 10,
20,000?
20,000. 20,000?
Yeah.
So that's 20,000 cubic feet. Now, by the way, look at this. Cubic feet over cubic feet cancels. I mean, this is just a number. It's a decimal. It's what?
0.16.
0.16. Do you want to make that a percentage error?
16%.
Well, then multiply by 100, and now it's 16%. And we could call that a percentage error if you want to. Hey, to me, percentage error and relative error are the same thing. Is that okay with you? Aren't they the same thing? I mean, one relative error is 0.16. Write it as a percent, and it's percentage error. My point is, though, they're both different from error. What was error? 3,200. I mean, that was the actual error, or approximated error. So anyway, 16% is kind of a lot, right? That's kind of a lot of error. Yeah. But you saw how I measured the room. You know, this is kind of fun. I'm going to finish this. Watch this. But this was a decent problem. You guys, there's a lot of good word problems in 13.4, kind of like this one. You need a formula. You need a total differential to approximate an error. And there's twists and turns that make them a little difficult sometimes. We'll have to practice a few of these. But before we leave today, one more little thing. What if, watch this. You know, what if we did the overestimated volume? In other words, what if I did the volume when it was 53, 42, and 10.5? Are you following me? If I did really use like the maximum possible error on each one of those variables, what would be this volume?
23373.
23373. Wait.
That's it.
23,373 feet cubed. Okay, thank you. Hey, hold on a second. What is the actual measured volume? Oh, that was the 50, 40, and 10. That was 20,000? Okay.
What about under error?
Yeah, so hang on. What's this difference here? Because this is kind of the change in the V. This is sort of a change in V, right?
3373.
Yeah, 3373. So
That's the actual.
3373. That's sort of the actual change in V.
Actual.
Is that approximately, what was our approximate? 3,200 was our approximation using the total differential. But this is kind of an actual. So that's a little off, right? But let's do the under one. Hang on. Let's do the under error. Yeah, watch this. What would that be? 47, 38,
9.5.
and 9.5. Everybody with me? What's this number, please?
16967.
And that change is what?
3033.
3033. Again, that's off. Watch this. You want to see the beauty of this? Average those two errors.
3203.
3203? Are you kidding me?
No.
Baby?
Oh, you get the jackpot over here.
Right? That's awesome.
Wow.
Maybe that's kind of what we're doing with this total differential. We're finding an approximation for the error. I'd call that actual over error and actual under error. I don't know what I'd call the actual error. I think I'd call some average of that the actual error, and that's darn close. Yeah, I like that problem. Hey, we'll quit today. You keep doing homework. And maybe, you could try some partial derivatives in 13.3, but if I was you, I'd get up to 13.4 and try a couple of these. These are fun. 13.4 problems.